We looked at the PK/PD of vancomycin and determined the loading dose. We used IDSA guidelines and population kinetics to determine an empiric dose and frequency. We also looked at vancomycin levels to select individualized vancomycin dose and frequency. We also looked at vancomycin dosing in intermittent hemodialysis. Now the next learning objective is given a patient receiving vancomycin, approximate vancomycin AUC. So remember that AUC is for a 24-hour period of time. In this example, we're showing you a Q8 dosing of vancomycin. So on the horizontal axis, you have time. So it goes from time 0 to time 24. And on the vertical axis, we have vancomycin concentration in the blood. If you give this vancomycin dose 3 times a day, or Q8, so you get a peak 3 times. And the area under all of this would be considered the AUC for 24-hour period. Now, if you get a single level, if you get just a trough, the question is, can you estimate how much the AUC would be? So because the AUC is the area of under the curve, if you have a trough of 10, you can say that this level never goes below 10. So you can say that the area under the curve is at least 10 times 24, which is 240. So this area is at least 240. And then you also have all of these areas at the top, which we don't know because we don't know what the peak is. So that's the issue. When you only get trough, you don't really know what the true peak is. So it only allows you to estimate what the AUC is. So we know that the AUC is at least 240. And remember that we want the AUC to MIC ratio to be at least 400. So if the MIC happens to be 1, we need an AUC of 400. Now this highlighted area is at least 240. So we're hoping that all of these area at the top is at least 160 to add up to 240. So that's where the recommendation of goal trough of 10 to 15 come from. So in a non-serious infection, if you have 10 to 15, so of course if you have 15 times 24 will give you 360. So now 360 is close to 400, and of course we have all of these area at the very top. So I'm actually very confident that a trough of 15 will achieve 400. So for a non-serious infection, the old guidelines recommend a trough of 10 to 15. And they're saying that if you achieve a trough of 10 to 15, you probably had an AUC of at least 400. You can be confident. Now, if you have a trough of 20 times 24, it's at least 480. So you definitely have achieved the AUC of at least 400, because you also have all of these areas. So at the very minimum, you have 480 plus all of these. So a trough of 20 is an overkill. So you definitely achieved an AUC of more than 400. Now the thing is, if you do between 15 and 20, so 15 would give you 360 and 20 would give you 480. So for serious infections, they said if you target the trough of 15 to 20, you're basically guaranteed to have an AUC of 400, and that's where those recommendations are coming from, which in the case of 15 to 20 could actually be overdosing. Now let's see the correlation between trough to AUC. So these guidelines from 2009 and 2011 said that you can use trough as a surrogate for AUC, because we know AUC is the PK/PD target for efficacy. So AUC actually determines efficacy. Trough really doesn't mean anything for efficacy. Trough only is meaningful for safety, which we will talk about in a little bit. But for efficacy, trough doesn't mean anything. So what they said was that they're actually using it as a surrogate for AUC, which is the actual parameter for safety. And they said that's because there's a significant correlation between trough and AUC. And when they said it's a significant, what they meant was that this is a statistically significant. So in this graph on the horizontal axis, we're looking at the vancomycin trough, and on the vertical axis we're looking at AUC, and here you have a scatter plot. And then you can actually get a Spearman P and correlation coefficient. So the correlation coefficient, or R, is 0.43, which means there's a 43, or let's say there's a 44% correlation between trough and AUC, which is horrible. That's worse than a coin flip. So there's only a 43 correlation between trough and AUC. And if you get the coefficient of determination, which is R squared, is only 19%. So that means only 19% of variation in AUC is determined by trough. And the p-value for it was significant. So they said there's a significant correlation between trough and AUC. But nevertheless, it's not a very good correlation because it's less than 50%. So what else can we do to estimate AUC if trough is not really a good surrogate for AUC? So one thing that you can do is use the general equation AUC equals dose divided by clearance. So especially if you have two levels and you actually calculated the clearance in the patient, you know the dose and you know the clearance, you can actually get the AUC. And now empirically, when you just starting the dose, you can't really know the clearance in the patient from levels because you haven't received levels yet. So you can actually use population kinetics. So there's this equation, the Moyes-Brother equation, that was actually derived from their patient population, that can actually estimate what the AUC would be empirically. So imagine you wanted an AUC of 400 and you know the patient's creatinine clearance. You basically solve for dose, and that will give you the empiric dose that will give you the AUC that you want. Now, a better way to do it is to actually use the multiple levels that we got in the patient to use individualized pharmacokinetics to calculate the AUC. For doing this, we can consider two areas. So the first area is the area during the infusion phase. So AUC INF, this is the first area, so for one dose. And this is basically using a trapezoidal rule. So you can imagine that this is a trapezoid and you're calculating the area for that trapezoid. So peak plus trough divided by 2 times the time of infusion. So going from this point to this point will basically give you the height of trapezoid if you consider this a flipped trapezoid, so to speak. And then you have the first base and the second base, which you can add together and divide by 2. And that will give you basically mathematically the area during the infusion. And then you need to calculate the second area, which is during the elimination phase, which of course also includes the distribution phase. But the AUC elimination phase is peak minus trough divided by K constant. And again, K is calculated from the two levels that we got from the patient. And then you basically add these two, so they will give you the AUC for one dose. And then to get the AUC for a 24-hour period, because this is AUC 0 to 24, you basically have to multiply by 24 divided by tau. For example, if your tau is 8, because you're giving the dose every 8 hours, 24 divided by 8 would be 3. So basically you multiply this AUC by 3, so that would give you the AUC for a 24-hour period. On the other hand, if you're dosing it every 24 hours, your tau is 24, so this basically gets canceled out. So these two areas will give you the AUC. Now, another thing that you can do, which is actually what the new 2019 IDSA guidelines are actually recommending, is to use the Bayesian approach. So now there are Bayesian software that are becoming pretty readily available and affordable. Bayesian software actually uses adaptive model that fits your patient with very high accuracy. And these models can either use a single level or it could use 2 levels. So using 2 levels is more accurate, but nevertheless, even a single vancomycin level is very accurate in predicting AUC. Bayesian approach actually uses the Bayes theorem. It quantifies the sequential relationship between the estimated probability distribution of an individual's patient pharmacokinetic parameters, so such as volume of distribution and clearance. And this is referred to as Bayesian prior. So the Bayesian prior basically uses population pharmacokinetics. So basically the things we did to calculate volume of distribution and clearance, to estimate what the patient's volume of distribution and clearance would be empirically. And then once you get the vancomycin level, either 2 levels or 1 level, you put them in the Bayesian model, and then from these two, you get the Bayesian posterior. So it basically revises that probability distribution that was population kinetics to adapt the model to the patient. And this allows AUC estimation, and it is very accurate. So I imagine that over the next few years, more and more hospitals will adapt Bayesian software. There are ways to build this software into Epic or other systems. There are also web-based versions of Bayesian software that can be used. So over the years, we will see more and more of Bayesian approach being utilized. Now, one last thing that I want to talk about is vancomycin continuous infusion. So if you were to, with intermittent infusion, I showed you that you can estimate what the AUC would be from the trough. Now, if you do a continuous infusion, if you start from 0 and you infuse the vancomycin dose over 24 hours. So you basically increase the time of infusion all the way to 24 hours. So within 24 hours, you actually get to the steady state. So you go from 0 to 24, and then at 24, you get a flat line because you're continuously infusing it over time. So then you don't get the peak and trough. You just get the flat line. So if you get the level at any time, that level is a random level, but it's also your peak and trough. So if you were to get the level of 20, your area you're no longer estimating what the AUC would be. The AUC would be exactly 20 times 24, which is 480, because you don't have the peak and troughs anymore. This is a continuous infusion. Now, the problem with continuous infusion is during the first 24 hours, it took a very long time to get to this. So you were underdosing for the first 24 hours. Which can be fixed by giving a loading dose. So if you were to just do the continuous infusion without the loading dose, you get this. If you do a single loading dose, that's the graph that you get, and then you do a loading dose and your continuous infusion, then you get this peak here, and then after 24 hours, you get a flat line. So that would be the best approach to get the right AUC. Now, however, there are advantages and disadvantages to continuous infusion. So advantages would be that it's effective PK/PD target attainment, potentially less nephrotoxicity because you don't get those high levels of vancomycin in there. You don't get those high peaks. It basically becomes once a day dosing because you're infusing it over 24 hours. So it's literally you change the bag every 24 hours. In fact, because you only do this every 24 hours and infuse it over 24 hours, this is oftentimes used outpatient. So it's convenient for outpatient parenteral antibiotic therapy or OPAT. Now, the disadvantage is that, a vascular line will be busy all day. So if you wanted to administer other antibiotics or other medications, really, a line would be taken. And ultimately, we haven't, studies have not shown a clear evidence of improved efficacy over conventional intermittent dosing. And the 2020 ASHP IDSA vancomycin guideline recommends continuous infusion may be a reasonable alternative to conventional intermittent infusion dosing when the AUC target cannot be achieved. So if you keep getting levels and you cannot achieve the AUC, then continuous infusion might be able to help you achieve those targets. If so, especially in critically ill patients, a loading dose of 15 to 20 milligram per kilo is recommended, followed by a daily maintenance continuous infusion of 30 to 40 milligram per kilo. And this is to achieve a steady state level of between 20 to 25 milligram. And this doesn't matter once you're at steady state. It doesn't matter if it's a random level because your peak, trough, and random are the same level.